Thank you. Good afternoon, everybody. So yes, I am an engineer at Airbus Defence and Space. I am the attitude and orbit control system and navigation architect of the JUICE project at Airbus. And actually, I am a lucky engineer because in the past, I had the chance to work for more than 10 years on the Rosetta mission, the European Comet Chaser mission, which ended last September by terminal descent toward the comet surface. And I proposed to Isabelle for this conference to give a talk about Rosetta, but she told me that, okay, it's already in the past, nobody cares about it anymore. Which I kind of disagree, but okay, never mind. So she wanted a talk about a future mission, and fortunately I am also working now on the JUICE mission. So JUICE means Jupiter Icy Moon Explorer, and it will be the first European mission to Jupiter. So just as a global overall picture, here is the ISA's legacy in the solar system, all the European missions from ISAE to the solar system. So we have been to the moon with a Smart One here. We have been to Mars with Mars Express, which is still flying, orbiting Mars. Of course, ExoMars has joined Mars Express since last year. It's not in this picture, but it's because it's not in the science division of ESA, but rather in the exploration division of ESA. We have been to Venus with Venus Express, which ended its mission because it depleted its fuel last year. And soon Europe will launch Bepi Colombo to Mercury in 2018, and a solar orbiter for a close-up observation of the Sun. Europe has also landed on Titan, a moon of Saturn, and the next step, well, will be JUICE. So JUICE will be is the first large mission of the ESA science program called Cosmic Vision, and the main objectives, I will come back later on it, are to study the emergence of habitable worlds around the gas giants, and to study Jupiter's system as an archetype for gas giants. So for Jupiter, one can say that everything started at the, not everything, but the most major step of Jupiter observation by humanity started in the early 17th century with Galileo. When he looked at Jupiter with his small telescope, he could see some bright spots near the Jupiter planet, and he found out that these bright points moved with respect to the planet. So first he thought there were stars, but actually looking at the relative motion of Jupiter with respect to the bright spots, he made evidence that obviously some objects were orbiting Jupiter. And it was the first time that a man could see a planetary system from outside, and it was also the first time that he could get the evidence that not every celestial body was rotating around the Earth. So it was a major step for astronomy and for Jupiter observation. Here is what typically he could see, or of course not with that accuracy. This picture was taken, I think, two or 3 years ago, during a conjunction of Jupiter and the Moon, and we can see, of course, the 4 bigger satellites of Jupiter on this picture. When then NASA sent the first spacecraft to have a close-up view of Jupiter, the first picture was taken by Pioneer 10 in 1973. And then the next mission was a flyby mission from Voyager 1 in 1979. This spacecraft took close-up pictures when on its route to Uranus, Neptune, and Saturn on its way to these outer planets. This is another picture taken by Voyager of the red spot in the atmosphere of Jupiter. And the first real spacecraft mission that gave close-up views of Jupiter and its moons was Galileo, launched in 1989 by NASA and orbiting Jupiter from 1995 to 2003. And thanks to this mission, we finally got close-up pictures of the surfaces of the moons of Jupiter. So you can recognize, of course, the volcanic moon Io, which is the first closest to Jupiter. Then Europa, with an icy crust here. Ganymede, also with an icy crust. And Callisto, with much more craters on its surface, meaning that this moon is not active. But Europa and Ganymede are for sure two ocean moons, so with an ocean right below the surface, the icy surface, and potentially two deep space habitats. And these are the main drivers for going back to Jupiter for this JUICE science mission. Here is another picture, the latest one we got from New Horizon when it flew by Jupiter in order to, on its route to go to Pluto in 2008. As you probably know, there is one spacecraft from NASA currently orbiting Jupiter. It arrived in July 2016, last year. Its name is Juno. It's a spinner here, and its main objectives are really focused on Jupiter itself. So the origin of Jupiter, the interior of Jupiter, the atmosphere, and the magnetosphere. It is not at all designed to study and in close-up to the Jupiter moons. It's rather focused on Jupiter itself. Here is a picture taken by its onboard camera with Jupiter and the four main satellites of Jupiter last year, just before its arrival to Jupiter. Here is another picture taken by its infrared camera of the Jupiter aurora. So now, a few words on Jupiter itself. Just to remind some orders of magnitude. So Jupiter is the biggest planet in the solar system, 10 times less big as the Sun, but 10 times bigger than Earth, as you can see here. And here is a view showing to scale the Jupiter moons with respect to the Earth and the Moon. So as you can see, Io and Europa have overall size of our Moon, and Ganymede and Callisto are bigger. They are closer to the size of Mars, actually. Here is a view of Jupiter interior. So scientists believe that there is a rock and ice core at the center of the planet, and then metallic hydrogen before the atmospheric layers, mainly composed of hydrogen. Actually, Jupiter could have been a sun. It was just not massive enough in order to start the nuclear reaction of the sun, but it's really close. It's really close to becoming a sun. So, what are the JUICE science objectives? I'm not a scientist, so I will not detail all these objectives, but I can present them to you. We want to address two themes of the ISAE's Cosmic Vision program. First, what are the conditions for planet formation and emergence of life? And then, how does the solar system work? So, for doing that, we want to perform detailed investigations of Jupiter and its system in all their interrelations and complexity. We want to study Jupiter as the archetype for the giant planets, not only of the solar system, but also of extrasolar system. As you know, we are discovering many gas giants around other stars. So by understanding better the Jupiter system, we can also extrapolate this to these new gas giants planets around other stars. And furthermore, we definitely want to focus on Ganymede as a planetary body and its potential habitat. We will not only study Ganymede, we will also investigate Europa and Callisto in order to have a complete comparative picture of all Galilean moons. focus on Ganymede here on this slide. So Ganymede is a natural laboratory for analysis of the nature, evolution, and potential habitability of icy worlds. The scientists want to characterize the ocean layers and detect putative subsurface water reservoirs. They want also to assess topographical, geological, and compositional mapping of the surface. They want to study the physical properties of the icy crust. They want to characterize the internal mass distribution, the dynamics and the evolution of the interiors. They want to investigate also the exosphere and study the Ganymede's intrinsic magnetic field and its interaction with the Jovian magnetosphere. And I have to mention that JUICE will be the first ever spacecraft to orbit the moon of another planet. This has never done before, and JUICE will be the first. JUICE will also study Jupiter system as an archetype for gas giants. So we want to characterize the diversity of processes in the Jupiter system which provide a stable environment at Ganymede, Europa, and Callisto on geologic timescales. Scientists want also to investigate the structure, dynamics, and composition of the Jovian atmosphere. So this will be done also by Juno, but they will do it again with JUICE. They want to study the circulation, meteorology, chemistry, and structure of Jupiter itself, and also investigate the weather systems and the mechanisms of transporting energy, momentum, material between the different layers. So really a complex planetology system that scientists want to study with JUICE. There are complex interactions between Jupiter and the moons through the magnetosphere of Jupiter mainly. So they want to investigate the three-dimensional properties of the Jupiter magnetosphere, an in-depth study of the coupling processes within the magnetosphere, the ionosphere, and the thermosphere. They want to study also the aurora, the radio emissions, their responses to the solar wind. And finally, they want to study the moon's interaction with the magnetosphere, the gravitational coupling, and the long-term tidal evolution of this Galilean satellite. Here, this is a schematic view, a theoretical view of the Jupiter magnetosphere if it was visible from Earth, so you can see how big this thing is. It's, of course, the most important magnetosphere in the solar system. This is a view of the aurora that we can see on the poles of Jupiter, with the some traces here are from the moons themselves. I think this is a trace from Io, and this one is from Ganymede. But most of all, with JUICE, we want to really focus on the Jupiter moons. And JUICE will not be the first orbiter that, the only orbiter that will be sent to Jupiter. As you may know, NASA has also a project which is named Europa Multi-Flyby Mission, or CLIPPER. And they want to focus this spacecraft on Europa. So it will perform 40 flybys of Europa, whereas JUICE will perform flybys of Europa, Ganymede, and Callisto, and at the end will orbit Ganymede as well. We will have two spacecraft, one from NASA, one from ESA, orbiting Jupiter in 2030. Here is a view of the Europa interior, with an icy crust of a few kilometers thickness, a subsurface ocean, and potentially some volcanic seafloor, which might be interesting for life. So this is why scientists want to focus on Europa and also on Ganymede. As you may know also, NASA has recently discovered and made evidence of potential icy plumes going away from the surface of Europa. So we might be able to detect these plumes in high resolution with JUICE and CLIPPER. This is a view of the Ganymede interior, which is kind of the same as Europa, but with a larger, thicker ice crust, then a saline ocean, and then an ice mantle. So scientists want to confirm this theory of Ganymede interior with juice. As I said, there is a magnetosphere around Ganymede. I think it's only there are only 3 planetary bodies with magnetosphere: the Earth, Jupiter, Ganymede, maybe 4. Mercury also has, I think, a magnetosphere. There are also auroras around the Ganymede. So, of course, JUICE, when orbiting Ganymede, will be able to perform high-resolution images and remote sensing of this aurora. So that's for science. So now I will rather speak about the spacecraft and the mission itself. So there are many elements in this mission, in this ESA mission. One element is, of course, the spacecraft. One other is the launcher, which will be Ariane 5. We need ground stations from ESA to communicate with the spacecraft. We need also an operation center, which is in Germany, Darmstadt, from ESA, in order to operate the spacecraft. And there is also a science operation center. So many elements to manage this JUICE mission. A few figures on this mission. So the industrial prime is Airbus Defence and Space, a few kilometers from here. We were selected by ESA in 2015, and we have built a consortium of about 80 European companies from 20 European countries. So a huge team to build the spacecraft. We have a mass at launch around 5 tons, with more half being propellant fuel, and 220 kilograms of scientific instruments. The main characteristics of this spacecraft is the huge size of its solar arrays. We need power at Jupiter, which is brought by the solar cells on these solar arrays, and we have about 100 square meters of solar arrays. And we bring with us 10 scientific instruments. Here are the science payload that we will carry on board. We have a visible camera system to take high-resolution pictures of Jupiter and its moons. And we have then several spectrographs in different spectral bands, infrared, ultraviolet, and sub-millimeter wave instruments. We also have on board a laser altimeter that will be able to measure with very high accuracy the distance from the spacecraft to the surface. And scientists want to discover from this whether to prove the presence of the ocean beneath the surface. We have a nice penetrating radar to study the interior of the moons, a magnetometer that will measure, of course, the magnetosphere of Jupiter and Ganymede. We have some instruments to detect and measure the particles around Jupiter. We have radio plasma wave investigation instruments and gravity science experiments. And here is the view of the spacecraft at its current design stage, if it works. It worked 5 minutes ago, so. So it doesn't work anymore, so I'm going to launch the movie from outside. So here is the spacecraft, a view of the spacecraft. So you can see, of course, these huge solar arrays, 5 panels per wing, in a cross configuration. The central body of the spacecraft is about 2.5 by 4 meter in dimension. We have a hidden antenna of 2.5 meter diameter, and we have, as you can see, a very long boom here in order to put the magnetometer instruments at the tip of the boom, such as its measurement environment is very clean, in order to measure the gravity, the magnetosphere of the moon and not of the spacecraft. And as you can see, we have several appendages for mounting the science instruments. If we take a look at the interior of the spacecraft, here it is, we have a large central cylinder which is able to sustain the loads at launch. Inside this cylinder we have two big propellant tanks of 1,600 liters each. And as you can see, the structure of the spacecraft is made of walls with cutouts in order to save mass, which is already very important on this mission. So if I go back on the presentation. So a few numbers and figures for the mission itself now, the mission profile. So as I said, we have a launch by Ariane 5 from Kourou in May 2022. Our interplanetary transfer to Jupiter will last 7.5 years. And we will inject into orbit around Jupiter in October 2029. Then we will perform multiple flybys of the Galilean moons, and we will have two Europa flybys, two flybys by Europa in 2030. Then we will start an observation phase at high latitude of Jupiter. And then we will also perform 13 flybys of Ganymede, 14 flybys of Callisto, before transferring to Ganymede for the end of mission in August 2031, with an insertion in orbit around Ganymede in December 2032. And at the end of the mission, we will be in a circular orbit at 500 kilometers altitude around Ganymede, which will last about 10 months. And the end of mission, which will be a controlled crash on the Ganymede surface, will be in September 2033. So, a few words on the challenges of this mission. There are some listed here. So, how to travel to Jupiter, how to navigate around Jupiter, how to control the spacecraft attitude and trajectory, how to communicate with the Earth, how to produce power on board, how to survive extreme temperatures, and how to survive intense radiations. So a few words on each of these topics now. First of all, the juice trajectory. As you can see, the best way to go to Jupiter is not through a straight line. It's by doing multiple gravity assists in the solar system at the planets of the solar system, so the Earth, Venus, and Mars. And here is a particular transfer profile from Earth to Jupiter using 3 gravity assists at Earth, 1 at Venus, and 1 at Mars. And because of this, of course, the trajectory is longer, but at least we save a lot of fuel, and we can therefore send more scientific instruments to Jupiter. When we arrive at Jupiter, we make several flybys of Jupiter moons, Europa, Ganymede, and Callisto, and then we end around Ganymede for 10 months. So it represents a trajectory with more than 6 billion kilometers, and we have to produce a velocity increment with the onboard propulsion system larger than 2,400 meters per second. So here is a little movie which doesn't work neither. So go back to the movie here of the mission profile. So you have seen the launch from Earth, and here we approach the first gravity assist at the Earth. A Venus gravity assist follows before a second gravity assist at the Earth. So you have understood that this is the spacecraft trajectory, and these are the planets orbiting the Sun. A last gravity assist at the Earth. On the right you can see the solar flux, high and lows, the delta V that we have produced, and the radiation dose inside the spacecraft vault. I'll come back to this later. And then the last arc of the trajectory, we go to Jupiter here, we approach Jupiter. here is the Jupiter orbit insertion with a zooming on the Jupiter system. I will come back to the insertion just after. So after the Jupiter orbit insertion, we have a very long first orbit around Jupiter lasting 9 months before coming back to Jupiter. And it is at that time that we start with multiple flybys on the Jupiter moon, starting with Ganymede, which is the red orbit here. Another flyby of Ganymede. And then the orbit gets closer and closer to Jupiter in order to have flybys of Europa. Here are the Europa flybys. And after the Europa flyby, we start a high latitude observation phase. As you can see, the inclination of the orbit around Jupiter increases in order to allow the scientists to observe the poles of Jupiter. Still by doing flybys of the Jupiter moons, especially Callisto. And then we start the transfer to Ganymede. What you can see on the right here is the delta V produced by the propulsion system of the spacecraft. When we insert around Jupiter, of course, there is a large delta V which is produced, and here the radiation dose that is increasing as we approach Europa. So here we are approaching the orbit of Ganymede, which is the red orbit here. And at the end of this phase, we will be able to insert into orbit around Ganymede. We do this to minimize the fuel consumption, which would be too high if we would go directly to Ganymede. Here, this is a zoom of the spacecraft orbit around Ganymede. We have first an elliptical orbit, then a circular orbit at 5,000 km distance from Ganymede itself. And after a few weeks, we will lower that orbit to a 500 kilometers altitude in order to have high resolution remote sensing of the moon. Here we have reached the 500 kilometer altitude orbit up to the end of mission, where we cannot avoid crashing on Ganymede because we don't have enough fuel to escape from Ganymede. So the end of mission is really a crash on the surface. So this was a view of the mission profile. Full zoom on the Jupiter orbit insertion. We will use the gravity from Ganymede in order to reduce the delta V that we have to produce for the insertion around Jupiter. So 7 hours before the burn of our main engine, we will fly by Ganymede. But there will be no science during this flyby because we have really to focus the spacecraft on its objective to get into orbit around Jupiter. So how to navigate now through the solar system? As you may know, we navigate by performing ranging and Doppler measurements from ground stations on Earth. But for JUICE, we have to enhance this by optical navigation at the Jupiter moons. So we have an optical navigation camera, and we take images with this camera of the Jovian moons against the background stars. And this allows to improve their ephemeris errors. And it's really mandatory to have this navigation camera on board in order to fine-tune the spacecraft trajectory for each flyby. For the spacecraft altitude, we have star sensors in order to perform altitude determination, which is a classical way. But for JUICE, we have a special feature for navigation. We will perform autonomous navigation on board during all flybys. We will track actually the limbs of the moons, the limbs that you can see here. We will track it on board with the navigation camera images in order to improve the spacecraft pointing guidance during these flybys, which will be a first also for a European mission. In terms of trajectory control, we have a main engine, a rocket motor of 425 Newton thrust and 20 smaller thrusters. And as we have already seen, there is more than 50% of the spacecraft mass at launch, which is fuel. The last movie is a view of Europa flyby, as if we were on board the spacecraft. So we will perform 2 Europa flybys at an altitude of about 400 kilometers. And this shows what the navigation camera will see on this, in this small frame here. And this is a view of the spacecraft flying by Europa during its mission. We will perform small scanning that are requested by scientists, because scientists want to scan the full planetary disk of Europa during the flybys. So the spacecraft will move in altitude in order to fulfill this need. And as you can see, as we are approaching Europa, the moon gets bigger and bigger in the navigation camera image. And the next phase is symmetrical with respect to the approach. When we depart from Europa, the same attitude will be maintained as for the approaching phase. So it will last about 12 hours before and 12 hours after the flyby. All the science instruments will operate to have a high-resolution remote sensing of Europa itself. So let me go back to the presentation. So we have seen how to travel, how to navigate, now how to communicate with the spacecraft. So on the spacecraft we have one high-gain antenna, fixed, not articulated. And we have a smaller medium-gain antenna articulated of 50 centimeter diameter. We need to communicate a power on board of about 50 watts, and we can ensure that a rate of more than 50 kilobits per second. And on Earth, of course, we use the ISAE ground station network around the world. There is one antenna in Spain, another in Argentina, and the last one in Australia, each one with a diameter of 35 meters. We have communication delays, of course, because we go so far from the Earth, so the communication delays will be up to 50 minutes. This means that we really need an autonomous avionics system on board in order to perform the mission. Not everything is autonomous, but a large part can be done autonomously by the spacecraft itself. We will be able to get 175 megabytes of science data per day and more than 250 gigabytes of science data over all the mission. With respect to power, here is the view of what NASA did for Voyager in 1977. At that time, they used a radioisotope thermal generator, so which based on plutonium material, which provides 470 watts at launch, and it's still alive after 39 years. But in Europe, we cannot use this technology because of political and safety reasons, so we have to use solar cells in order to produce power, even at Jupiter, and this is why we need so large solar arrays. We have more than 27,000 solar cells on board, and there are special solar cells designed to survive low temperature and high radiation doses, with an efficiency of 28%, and this efficiency decreases as the radiation dose increases. And at the end, we will have 800 watts on board the spacecraft. Now, a word on the thermal aspect. So we will have to survive extreme temperatures because we go to swim by Venus at the start of the beginning of the mission, where we have a very high solar flux, twice that of at the Earth. So in this phase, we will use our high-gain antenna in order to as a sun shield. And we will have a constrained spacecraft altitude, and the antenna temperature will reach about 180 degrees Celsius. But when we get to Jupiter, then the solar flux is 25 less than at the Earth, so only 50 watts per square meter. And furthermore, we will experience long eclipses by Jupiter, and then the antenna will reach temperature down to minus 200 degrees Celsius. So we really have to be very careful in the spacecraft thermal insulation in order to survive these extreme temperatures. And of course, we cannot afford a large heating power on board because of this very demanding power budget. And the last challenge that we have to face, or at least of the most challenge that we have to face, concern the radiation environment. So as we have seen, Jupiter has a large and intense magnetic field, and energetic particles from the solar wind, the cosmic rays, and the Taurus are trapped within this magnetic field. So therefore, they are mostly high energy electrons, and Europa flybys are the most critical in terms of radiation environment because they are close to Jupiter, and all these radiations are very potentially harmful to the spacecraft electronics and exposed material because they can produce electronic components degradation over time. They can produce also spurious events like resets of the electronics. There is a risk also of electrostatic discharge and disturbances to the science measurements. So we have to perform and to implement mitigation measures in order to survive this radiation environment. And the main three mitigation measures that we have is to fine-tune the trajectory and to optimize the trajectory in order not to approach too close to Jupiter. So this is why, for example, we don't go to Io, because it's too close to Jupiter and it would be too severe in terms of radiation environment. We have also, the second mitigation measure is to select only radiation-hardened electronic components, which is not easy. And the third one is to implement shielding on board. So I have not shown you to with the spacecraft configuration, but we have installed all sensitive electronics inside two shielded vaults on the spacecraft in order to protect these sensitive electronics from the radiation environment. So it's the major challenge that we have on this JUICE mission. And okay, I would like to finish with the next step. So as you have understood, JUICE will be a flyby and orbiting mission around Ganymede. And the next step will be to land on the surface of Jupiter moon. And we have proposed with Michel Blanc, a scientist from IRAP, we have proposed to ESA for future mission collaboration with NASA, between NASA and ESA, in order to carry a Europa lander that we can see here to the surface of Europa. So our proposition is to build the spacecraft that will carry this Europa lander and to provide this spacecraft to NASA by ESA, and the Europa lander will be a NASA Europa lander. So this mission, if everything goes well, could launch in 2025 sorry, and follow the orbiting mission that we have designed with JUICE. So we all hope to see this mission, but not in a very long time after today. So thank you very much, and if you have any question, please ask. No question. Yes.
Why are there several radiations on Jupiter?
Why?
Why are there several radiations environment?
Because Jupiter has a very strong magnetic field, so all the particles coming from the sun, coming from solar wind, or coming from Io, you know that Io is a volcanic moon, so many particles are emerging from Io volcanoes, and these particles get trapped in the magnetic field. So this is why there is a severe radiation environment with energetic particles that are trapped in this magnetic field. Yes?
what is the total dose that you're designing for your spacecraft during the lifetime?
Inside the spacecraft walls, the total dose is, we designed the electronic components to be radared to 50 kilorad. 50, yes. Thanks to the vault, which are shielded. But outside it's much more than this. Yes, it's got to megarad. The material has to survive megarad radiation dose. Yes.
When did the mission begin?
So we can say that this mission really originated 10 years ago with these advanced studies, and was decided, I think, 4 years ago by ISAE to enter in development phase. Yes?
How do you evaluate the gravitational fields of other planets? For example, you are using the gravitational effect of Io and other satellites of Jupiter.
Yes, it's the same as when we perform a swing by of Earth or Venus, during the transfer to Jupiter. We use the gravity of and the motion of the planet around the Sun in order to modify the trajectory of the spacecraft. So by modifying this trajectory just by flying by this gravity field, we save a lot of fuel, and this allows to bring more mass, more useful mass at Jupiter. So it's the same principle around the Earth or Venus and as around Jupiter moons. It's the same principle of gravity assist. Yes?
Why do you plan to finish the mission by crushing the device onto the surface?
We would like to not to crash. We would like to go away from Ganymede and fly by other moons, but it's a constraint of fuel that we have on board. We cannot afford bringing more fuel on the spacecraft because it would be detrimental to the science instruments mass. So we have no way to escape Ganymede after we get into orbit around it. So, and as we are authorized to crash, because Ganymede is not as sensitive as Europa or Mars for what concerns the science life emergence, so we can crash on Ganymede, and we have no way to avoid this crash. So it will end this way.
What instruments will be used to monitor the activity of the moons?
As I said, and as I showed, there is a series of science instruments here. So all these instruments, we have a visible camera system, spectrographs, laser altimeter, ice-penetrating radar. All these instruments will be used for remote sensing of the moon. So a series of 10 scientific instruments in different domains. Yes?
What's the probabilities your spacecraft actually launched in May 2022?
Well, it's a good question. It depends who you ask. We are confident now that we are in good shape to meet that date. Of course, there is a lot still to work on and a lot to do before we can fully know whether this will be achievable. But today, on the paper, we still meet that launch date. We are now at a review stage with ISAE, the preliminary design review of the spacecraft. And the conclusion today is that this launch date is achievable. But of course, if we get several difficulties in developing all the technologies that we have ahead of us, then of course this will change. But today, it's feasible. It's tight, but feasible.
What kind of duration and frequency of the launch window are you looking at for having so many gravity-assisted changes?
Actually, we have a classical launch window of typically 3 weeks, but we have several dates. The first one is in May 2022, but if we miss that launch date, we can launch the year after. But if we launch the year after, for example, the transfer to Jupiter will be longer. 9 years or 8 years, 9 years instead of 7.5. So this is why we prefer to target the first launch date. But if we miss that one, we have other opportunities during typically 4 to 5 years. Yes?
What theories are expected to be tried by this mission?
What, sorry?
What theories are expected to be tested by this mission?
You mean science theory or?
Science theories?
Well, as I explained, I am not a scientist, so I cannot too much explain it, but they want to confirm the presence of the oceans below the surfaces of Ganymede and Europa, and they want to better understand the full Jupiter system as a mini solar system, I would say. So there is a lot to learn at science level going there.